All right, I'm going to roll through practice 1.3a number 4. Problem number 1. A car that we're labeling A moves to the left with a speed of 40 kilometers per hour. So we have car. I'm going to draw a good picture of a car here with A. It moves to the left with a speed of 40 kilometers per hour. It says another car, B, moves to the right with a speed of 60 kilometers per hour. Find the relative velocity of B with respect to A. So both of these velocities are versus somebody standing on the street. Somebody standing on the street says, whoa, that car is going 60 kilometers an hour. Somebody standing on the street would say, whoa, that car is going 40 kilometers per hour. But now, if you were in car A, how fast does it appear that car B is moving? There's two ways to do this. One of them is just to think about the fact that even if you were stopped in car A, car B looks like it's coming at you at 60 kilometers an hour. And when you're traveling towards it, now you have two oncoming vehicles. It's going to appear that car B moves with a speed of your speed plus whatever it's coming, right? The two cars are closing on each other. They're moving towards each other at a speed of 60 plus 40. That's 100 kilometers per hour. So from car A relative to car A, or with respect to car A, it looks like car B is moving towards you with a speed of 100 kilometers per hour. The velocity of B with respect to A equals 100 kilometers per hour in that direction. There's another way to do this, where we would take both of these vectors and put them both with their tails at the origin. In other words, if I create an origin point here, I could put this car's tail at the origin, and that's B. And then I could put this car's tail at the origin, and that's A. And just like we did with displacement, where is B with respect to A? Well, with respect to A, if you're standing at A, B is 100 that way. And that is the velocity of B with respect to A. All right, so either way, just kind of making sense with it in your head, or doing the same vector manipulation that we used for displacements, saying, Peter was over here and Linda was over here. It's like Linda's position relative to Peter was that, where we put both of the tails starting at the origin. You can do the problem that way as well. Next up, boat A heads east at 7.2 meters per second. So boat A heads east at 7.2 meters per second. Boat B heads north at 5.8 meters per second. So this guy is kind of trucking that way. Boat B is kind of heading north here. It's going 5.8 meters per second. All right. Both of these are measured by an observer fixed in one location. It says determine the following. What is the velocity of boat B relative to boat A? So in other words, when you're on boat A, what does it look like boat B is doing? Which way does it look like boat B is going? All right, well, we can solve this problem just like we did the last one with putting both of our vectors starting at the origin with their tail on the origin. The vector for A is 7.2 this way. That's the location of A. Now I know that they're velocity vectors, but we can think of them almost in terms of like displacement at this point. But B is 5.8 this way. So any vector manipulation that would work for displacement will work for any vectors that we're adding. It says find the velocity of boat B relative to boat A. So if you're at boat A, in this spot here, what is the velocity of boat B? What does it look like? Well, it looks like boat B is going that way. And in order to find the magnitude of that, we would do Pythagorean theorem, that the velocity of B with respect to A, we have the velocity of B with respect to A, the magnitude of that vector would equal, well, that squared is equal to A squared, 5.8 squared, plus B squared, 7.2 squared. And we could solve for the velocity of BA. So we have 5.8, I got turned on, 5.8 times 5.8 plus 7.2 times 7.2. And then I need to take the square root of that. Oh, not that button. Was it 85.2 or something like that? 9.23. So I get that the velocity of B with respect to A is 9.23 meters per second. And then you might also want to know what this angle is. What is that angle theta? Because in order to represent a velocity, I need a magnitude, the magnitude of velocity of B with respect to A, and I would also need a direction. Well, the tangent of theta is the opposite over the adjacent, so I can say that that angle theta, just like we showed before, is going to equal the inverse tangent, and you can look back if you want to see how we got this, of the opposite 5.8 over the adjacent 7.2. So what is that? All right, let's do that. So I'm taking the inverse tangent, that's second tangent, of 5.8 divided by 7.2, and I get 38.9 degrees. Rock on. I might say that that angle right there, if this direction is west and this direction is north, I might call that angle 38.9 degrees north of the direction west. So I could represent VBA is equal to 9.23 meters per second. And then I could represent this angle here as 38.9 degrees. Or instead of drawing a picture showing the angle, I could say 38.9 degrees west of north. Excellent. It says find the velocity of boat B relative to boat A relative to boat B. Well, in this case, we could use the same drawing, but this time we're going from B to A. So we might have the same drawing, but now we're going from B to A. So our reference point is boat B, and we're looking for boat A, and that's just the same vector, only this direction. All right, well, the velocity of A relative to B is going to equal the same magnitude, 9.23 meters per second. And now this angle here represent it this way, that angle there is going to be our 38.9 degrees. Or we could say 38.9 degrees south of east. Excellent. You know, this problem somewhat makes sense because when you're in boat B and you're looking at boat A, from the point of view of boat B, boat A looks like it's moving this direction based on boat A's velocity. Sorry, looking here. So from boat B, A looks like it's going this direction, that's east. And that's due to A's velocity. And due to B's velocity of going north, you're driving away from boat A. It looks like it's also going south to you. So A's velocity makes it look like it's going east. B's velocity, the boat you're on, makes it look like it's going south. And so it's going southeast. All right. Take a look at this last problem, number 3. Rain comes down vertically at 8 meters per second during a rainstorm. A girl runs towards the right with a velocity of 11.3 meters per second. Find the velocity of the rain relative to the girl. Draw a picture to clarify. Right. So this raindrop, it is falling with a velocity of 8 meters per second. And the girl is moving with a velocity to the right. So this is the raindrop. The girl is moving to the right with a velocity of 11.3 meters per second. And that's the girl. Find the velocity of the rain relative to the running girl. So the girl feels like the rain is going both down from the girl's point of view. The girl feels like as she's running this way, this is her running. As she's running this way, she feels like the rain is not falling straight down in front of her, but rather she feels like the rain is traveling this direction. You know, the rain is actually hitting her right in the face as she's running into it. All right. Well, let's figure out what the velocity of the rain is. We have a triangle here. One side of 8, the other side of 11.3. We could find the velocity of the rain relative to the girl, we could say, as the hypotenuse of that triangle. The velocity of the rain relative to the girl squared is going to equal the velocity of the rain squared plus the velocity of the girl squared. All right, so velocity of the rain relative to the girl is equal to the root of the velocity of the rain, 8 squared, plus the velocity of the girl, 11.3 squared. Let's do this. So we're going to take the square root of a bunch. We got 8 squared plus 11.3 squared. 13.8. Now, that is really just the magnitude of her velocity. I'm sorry, of the rain's velocity relative to the girl. We should find also the angle. So we might want to find this angle here, let's say. And we would do that using the fact that the tangent of this angle is equal to the opposite 8 divided by the adjacent 11.3. In other words, the angle theta, if we call that angle theta, would equal the inverse tangent of the opposite 8 divided by the adjacent 11.3. Let's do that. Second tangent, inverse tangent of 8 divided by 11.3 gives us 35.3 degrees. And that's this angle here. So we could represent our whole velocity. The velocity of the rain relative to the girl is equal to 13.8 meters per second. At an angle here of 35.3 degrees. Excellent. All right. That's practice 1.3 and number 4 wrapped up.